Welcome everyone to the Metrics International Forum. The forum is organized by the Meta Research Innovation Center at Stanford, or for short, Metrics. The center is directed by Joan Ioannidis and Steve Goodman and is a research group and fellowship program dedicated to finding ways to improve the validity and transparency of scientific research. I'm Lina Koppel. I'm a visiting postdoc at Metrics, and I will be today's moderator. All of our international forums are recorded and can be accessed on our website. Please mute yourself during the talk and keep your questions until the end, or write them in the chat during the presentation. Our presenter today is Rachel Heyard, and Rachel holds a PhD in biostatistics and is currently a postdoctoral fellow in meta-research at the Center for Reproducible Science at the University of Zurich. Her research interests include developing and testing new approaches for allocating research funding, statistical methods in research, and improving reproducibility and the uptake of open science. So if you're ready, Rachel, we can start.
I am. So hi, everyone. Hi from my side too. And thanks for the nice introduction, Lina. Also, thanks for the organizers of the Metrics International Forum for giving me the opportunity to present my work to you today. So today I want to talk about some recent work of mine and Leonard Hell's, where we're using meta-regressions and more specifically location scale meta-regression in order to explain shrinkage and heterogeneity in large-scale replication projects. So this is while the preprint is already published on the Meta Archive, and you should have gotten the link with a meeting invitation, I think. If you didn't, just let me know later. So we submitted this for publication and are currently going through waiting for our next reviews. So any feedback is very much welcome to improve our work and get this work published. However, before diving into the more technical methodology, I also a little heads up. I'm a bit afraid that this presentation is going to be a bit more technical than maybe the usual metrics talks, but I hope to guide you through the technical details, and I hope that you still get the gist of why we're trying to do this using a case study. So I'd like to start by just defining all these concepts that you see in my title so that we're kind of on the same page and it's easier to understand and digest. So let's start with the definition of replication. One would think that everybody knows what a replication is that is listening in this talk, but the more I am doing research on these kind of topics, I realized that we're not all talking, we're using the same words, but we don't always mean the same thing by that. So I'd like to start by really defining what I and my co-author mean by replication when we're talking about replication. So this is more specifically direct replication, and we are, for our work here, using the definition from the National Academies of Sciences, Engineering, and Medicine. So in this case, a replication is a study that follows the methods that were presented in an original study as close as possible. And this replication study retrieves new data in order to achieve consistent results using the same methodology. So it's different data compared to the original study, but the same methods as in the original study. Then large-scale replication projects. So when we're talking here about large-scale replication projects, we're talking about projects that select a set of influential papers from a specific discipline, for example, psychology or economics or cancer biology as more recently, and then tries to replicate this set of influential papers. And again, here specifically, we are talking about many phenomena, one study projects. And these are kind of in contradiction or in contradiction to maybe the many labs or many analyst studies. So in the many phenomena one study projects that we're interested in, we have a lot of original papers, and each of these original papers are replicated once. right? So many originals and one replication per original. While in the other, like many labs or many analysts, you have maybe one phenomenon or a hypothesis or a data set that is analyzed by many different teams. So these are a bit different, and they are kind of answering a bit different, like questions that are a bit different. And as examples for replication projects, I just list here the replication process psychology that you're probably all aware of, but also a smaller project, which is the replication project in experimental economics. And yeah, so these are also the two projects that we're using in our case study. All right, the next word that I think needs a bit of an explanation, what we are specifically meaning by this, and this is shrinkage of effect size here. So usually we're in this context of replication projects, we quantify shrinkage as being the relative difference between the effect size of the original and the replication study. And this is observed in almost all of the large-scale replication projects. And what I mean with this is like that there is shrinkage, so that the original studies find an effect that is larger than the replication projects. And if you're looking here at this picture, a picture like this you've probably seen before. So this is specific for the replication project psychology. And on the x-axis, we have the effect estimates of the original study. And on the y-axis, the effect estimates of the replication study. So if we had no shrinkage or like almost no shrinkage, and these studies would find more or less the same effect, all these points would be kind of clustered around this diagonal line. However, we see that most of them, about 80, well, more than 80% of these points are actually under the diagonal line, meaning that the original effect is larger than the replication effect. So this is what we call shrinkage. Yes. And it's you often discussed in the literature when authors talk about shrinkage of effect size, they usually attribute this to questionable research practices and biases, specifically publication bias present in the original study. So that we would assume that maybe because of these practices and biases, the effect that we find in the original study is inflated. So it's exaggerated, it's too big. While then the replication studies, they're most of the time designed a bit more rigorously. They are better powered, etc., to find an effect. And we would think that the effect is kind of more robust, so to say, and therefore smaller. Then the last concept or last word that I want to define for this talk is the heterogeneity. And here specifically, we're talking about between original replication study pair heterogeneity. So it gets a bit complicated and long. That's why it just says heterogeneity in the title. But this is essentially the variation that we see in the magnitude of the effect size difference in the different study pairs. So the effect size difference would be the difference between the original and the replication effect size. And there's just a lot of heterogeneity in these differences in the replication projects that we have looked at. All right. So this is in contradiction with maybe within original replication study pair heterogeneity, which would be the heterogeneity within a pair, so between the original and the replication project. Yeah. Okay. So let's get to kind of the problem and the aim we're trying to address with our work. So again, for this audience, it might be a repetition of things that you've already heard, is that these large-scale replication projects have overall estimated low reproducibility rates across research fields. So you've seen there's the reproducibility project psychology and also one in economics. There's others in cancer biology. So they all looked at different fields, but all of them find low reproducibility rates, or at least claim that. And also, it doesn't matter which reproducibility metric we're using to decide on like a percentage of reproducibility. So most of these like headline reproducibility percentages, like, oh my God, there's only 36% of findings that replicate. These kind of things are usually based on the significance criterion, and this is the with a significance criterion, we would want to find a significant finding in the original and in the replication study that goes in the same direction. And even if we're using other metrics for reproducibility, we always find these low reproducibility rates. Right. So we can say, and like we say, and others before us also did say, that there's this shrinkage and the difference in effect sizes of the study pairs included in replication projects. This is very heterogeneous, so it can go in either direction, and there's larger, like more shrinkage for some study pairs, less shrinkage for others. And overall, if you now want to kind of pool all of this heterogeneous data together and ignore between study pair heterogeneity, you might run into a problem. But this is actually what is being done, because at the end of the day, if you're doing a replication project, you want to kind of pool everything together and come up with that one magic number. And we say that this is challenged by between study heterogeneity. All right, so therefore, we are wondering whether we can use location scale meta-regression on one hand, in order to understand what the primary drivers of shrinkage and heterogeneity in these replication projects are. But on the other hand, once we understand this, when we're planning another or future large-scale replication project, can we then anticipate what levels of shrinkage or amount of heterogeneity we expect to see? And this can help us in the planning of our project. Good. So now I already mentioned that we're using the RPP, which is the replication project psychology, and then the replication project experimental economics in our case study. And so these are, in this figure, you see simply these differences that I mentioned before, these differences in effect size. So the original effect size minus the replication effect size. And they're all ordered depending on their magnitude. And each of these points stands for one replication, original replication study pair. And you can see that it's kind of the same data that you've seen in the other picture. So now we're just looking a bit at something a bit different. We're looking at the difference directly and also at the confidence intervals of these differences. And now we're comparing this here with the zero line, and we see that most of these differences are positive, so above zero, meaning again that there's shrinkage in our data. The original effect sizes are larger than the replication effect sizes. But we also see that there's a lot of variation in these differences, like this heterogeneity. This can really be very high or low, closer to zero, less close to zero. So they can go all over the place, but at the end of the day, we want to kind of merge this data all together. All right. So before going into the details of this modeling, just trying to keep this a bit simple. So now we've just seen that there seems to be shrinkage in our data. There also, we see a lot of heterogeneity in these differences. We can actually test this with an overall test of heterogeneity. So again, just sorry for a bit of mathematical notation, but at the end of the day, what you want to do is we just already looked at these differences, the estimated difference in effect size, and we can also compute the standard error of this difference. And then this gives us the squared standardized difference, which is also often called the Q statistic. And if we then sum these up, we can do an overall test of heterogeneity in the replication project using this property that this kind of follows as a chi-squared distribution under the assumption of no heterogeneity. And then if we look at this in our case study again, so what you see here this is just kind of a histogram of these Q statistics for the for each study pair. And this should follow a normal distribution. And you can see again that they are kind of skewed towards larger standardized differences. And this kind of links to shrinkage. And then on the second plot here, you see the p-values or the histogram of the p-values of the individual Q statistics of the study pairs. And then we computed this overall p-value of for a test whether there is evidence for between study pair heterogeneity in our data. And we would reject this null hypothesis. So we would assume that there's evidence for between study pair heterogeneity. Sorry, I'm repeating myself. All right. But now we say, okay, there is some evidence for heterogeneity. Well, can we actually quantify this? And this is pretty straightforward. And I'm going to present two different ways or versions of quantifying this heterogeneity. The second one might be the one you're more familiar with, so bear with me. The first one is this multiplicative heterogeneity phi, which we define by kind of looking at the distribution of these differences that we talked about before. And then here in the variance part of our distribution, we find this phi, which is now the multiplicative heterogeneity. So it's a multiplicative variance inflation parameter. So we're inflating the variance by this parameter. And in order to compute this phi, the only thing we have to do is we're using a weighted linear regression. So it's really pretty straightforward, just doing a weighted linear regression on these estimated differences with a constant as the sole variable. And as the weights, we're using the inverse of the variances, which ensures also that more precise study pairs have more influence. And then this phi is very straightforwardly estimated as the mean squared error of the model. And if we don't have any heterogeneity in our model, phi would be 1 in the absence of heterogeneity, and otherwise it is larger than 1. The type of heterogeneity that you might be more familiar with is the additive heterogeneity, which is, the only thing that changed here in this formula is there's a plus now for the heterogeneity, and it's called now tau squared. And tau squared is what you get if you are performing a random effects meta-analysis. I'm sorry, here I have problems with my bullet points. I changed something last minute, so that was not a good idea. But yeah, so if you're running a random effect meta-analysis, using the meta4R package, you're actually using an additive version of the heterogeneity. So you can directly estimate tau squared using this random effects model. And in the absence of heterogeneity, tau squared would be 0, and otherwise it is larger 0. So let's get back to our data to make sense of these formulas and see some numbers. So what you see here is just the kind of the output of these two models on our data. So for the multiplicative and the additive model, we find this intercept, which is positive, and also the confidence interval of both intercepts is larger 0, so does not include 0. So this is again related to shrinkage, because the average, on average, the original effect estimates are larger than the replications. So that's what we also see here. And then we have a heterogeneity, multiplicative heterogeneity of 2 and the additive heterogeneity of 0.02. So both of them are larger than 1 or 0. So we would say that there seems to be some heterogeneity in our data. And we now quantified it, so we could essentially put it back into the formula. So this kind of doubles the variation in the data due to heterogeneity. So it's a bit easier to directly interpret the multiplicative model, but the additive is the one that is more widely known, and that's kind of why we decided to do both, because it's a more methodological paper, so we could do both. And yeah, again, it's this one is the additive version is more widely known, while we believe the multiplicative is easier to interpret directly, and also they have though other underlying assumptions. So in the additive model, oh no, I start with the multiplicative model. The multiplicative model assumes that there is one common effect size difference, which is actually maybe very kind of nice for the replication setting, where we are well, in our case, the replication setting of the types of replication projects that we're looking at, where the replications are following usually a protocol that is very, very close to the original study. So therefore, the assumption of the multiplicative model might actually be closer to what we're actually looking at, or what we would hope to see, let's say. All right, so now we use these models, which are actually already meta-regressions without any covariate, but we now want to start with these kind of baseline heterogeneity parameters or values and see whether we can reduce those if we are adding variables or location covariates in our model. And this is actually very straightforward. So let's say, well, like once we already have done what we did before. So let's just select or select a set of P variables, covariates, and these are now called the location covariates because we're interested in the location, which is a link to shrinkage, the location of our model. And if we're using the multiplicative parameter or the additive parameter version of the heterogeneity, it works exactly the same. So we just add these covariates in our model as such, so in the linear predictor. So it's pretty straightforward. And both of these things are also very easy to implement, both in for the additive version with the RMA package and actually the multiplicative version just with base R. And then, however, what we get out is not directly the heterogeneity, it is the residual heterogeneity, multiplicative or additive. And this has been defined as the variability in the true outcomes that is not accounted for by these moderators included in the model. And then we actually need some, if we want to go back to our case study, we need some covariates, right? And we haven't talked about this yet. But the data we're using this data because Altmate and colleagues also use this data, and then they used machine learning models to predict reproducibility, to see if they can predict reproducibility. And they measured reproducibility using the significance criterion that I mentioned before, and they used covariates to do so. So what they actually did, they manually collected 25 covariates for each of the study pairs that were included in these replication projects. And they also did this for 2 of the many lab replication projects. So we only use the psychology and experimental economics projects. And they shared this data on the Open Science Framework, so we could reuse it. So we're very grateful for these authors to do that. However, they used 25 covariates for, well, we have now 25 covariates, but we only have about 87, I think, study pairs. So this is not enough data to just include this, all of these covariates in our models. So therefore, we already did like a little pre-selection, which might be a bit arbitrary. It's just like what we thought would be the most interesting covariates of these 25. That we kind of pre-selected. So we decided to investigate the usefulness of 9 continuous covariates and 5 categorical covariates. So these covariates that were selected by Altmate, They were mainly features of the original study design and also of the replication study design. So all of these things were kind of known before, or should have been known before the replication was conducted, so that they could predict the outcome of the replications, of course. But they were also features or demographics of the original authors and the replication authors, which might sound a bit odd, like for example, the share of male authors on the author lists of both original and replication projects, or the seniority of these authors, etc. But there were also covariates really related to the design of the original and replication projects. For example, were these experiment in the original and replication project done in the same language, because they were mainly psychology projects, or conducted in the same country. And we decided to also do some transformation with the continuous covariates. For example, we log transformed the citation numbers, and also the average author citations. And then we did another transformation on the kind of the strength of the evidence of the original findings. So we used the inverse, the squared of the inverse of the squared Z statistic of the original study. And we did this because from previous work in my group, it looked like this. Well, this was to be found to be linked to shrinkage. And so the more significant your study, the original study, the less shrinkage there should be. So we also wanted to test this in our data. All right. So now, so I mentioned we have 14 covariates now for 25 study pairs. No, sorry, 14 covariates for 87 study pairs, which might still be a lot. And therefore, we did some model selection in our paper. And we followed Sina et al., who said that one could use information criteria also in meta-regression and also in location scale meta-regression. So we decided to just go with the AIC. And what you see here in the green lines for both the additive and the multiplicative model, we have for each of the number of covariates that would be added to our model, the minimum AIC. And we then look for the minimum AIC because that's supposed to be the best predictive model. We find that 6 covariates should be added in the multiplicative, but also in the additive model. And these were conveniently the same covariates in our case. And how does this look now in our data? So this is just the table with like the last or the final model for both multiplicative and additive heterogeneity version. So we were able to reduce the heterogeneity quite drastically. So we went from about 2 for the multiplicative heterogeneity to 1.2 afterwards. So this is now the residual heterogeneity for the multiplicative model, and the additive model is also got very close to 0. And then we can also interpret these coefficients of the model a bit. So the intercepts of both models are very close to 0. So there's taken all of these covariates into account. We kind of were able to explain the shrinkage factor in a sense, because there's no difference anymore after you take all of these covariates into account. And also importantly to note is that the coefficient estimates of these models, they're very similar. So almost, sometimes even more or less exactly the same. So we can just interpret one of them. And I mentioned before this Z statistic, the inverse of the squared original Z statistic. And we had the assumption that the more significant, the less shrinkage. And this is actually confirmed in this case study. So there is a positive association between shrinkage and less, yeah, exactly, shrinkage and less significance because of the inverse, right? So now we only looked at the location, and I think I never mentioned, but like location is really about this like first bit of the of our model, so where we're interested in shrinkage. And now we didn't yet, well, we managed to reduce the heterogeneity, but we didn't talk about like really explaining it because we still have like for any covariate combination, we always have this one heterogeneity. So are we able to relate, well, thanks to location scale meta-regressions, we're actually able to relate covariates to the amount of heterogeneity in our outcome. So that's really what we want to do. So it works again similarly. We first have to draw or come up with a set of scale covariates. So these are covariates for the scale, therefore scale covariates. And to link these scale covariates to our heterogeneity or our scale, we use this property. So now our heterogeneity, so it is the multiplicative and the additive version, they are not a constant anymore. Instead, they are this like sum of our covariates, and they're on the log scale just to ensure that they're positive. And also this is easily implementable. So it is implemented in the metaphor package in R. And if you can also, in order to, so this is for the, for the additive version of the heterogeneity, and for the multiplicative version of the heterogeneity, we have to use this GAML SS package, which stands for generalized additive model for the location, shape, and scale, I think. But we have to introduce an offset because of the weighting, but it's pretty straightforward still. Yes, and then we did kind of the same little model selection exercise also for the scale coefficients as we did for the location coefficients, and then found a final model, which is then this. Actually, we now have for each of these covariates, we have location coefficients, but also for some of them that were retained in our final model, we also have scale coefficients. And like you don't see a line for heterogeneity or residual heterogeneity because, like I said, it's not a constant anymore. These are now dependent on the study pair at hand or the covariates that are going in there. And therefore, I try to interpret the multiplicative heterogeneity with an example here. So what you actually do is, so the scale coefficients, I said that they are like the scale is on the log scale. So you essentially have to take the exponential of these coefficients to get to the heterogeneity afterwards. So if we have an average study pair, like, yeah, an average study pair that uses the same language in both experiments, so in both the original and the replication study, the residual multiplicative heterogeneity would be about 1, so we wouldn't have any heterogeneity. So these study pairs with same language experiments would have a certain shrinkage. The location might be, like they have a certain difference, but it is no heterogeneity left. And then on the other hand, for an average study pair that does not use the same language in both experiments, the residual multiplicative heterogeneity is larger 1, so it is 1.2. So this is how you would interpret these results. All right, so anyway, I'm almost out of time. So just to come to a discussion and any limitations. So what we did here is more of a proof of concept that location scale meta-regressions, they're useful in order to put the amount of shrinkage and heterogeneity that you might see or observe in replication projects more into contexts. And very specifically, these results or future results using such a methodology could inform the planning, but also the interpretation of future replication projects. So first, when authors are planning a replication project, they might already expect the amount of or have an idea of what shrinkage, how much shrinkage or heterogeneity they expect in the effect size differences. And this could also influence the choice of the replication success metric. So if you expect that because of the design of your replication project, the effect sizes in the replications will be very different. There will be a lot of shrinkage compared to the original. Then, of course, it doesn't make sense to use a reproducibility metric that decides whether there's a replication success based on having the same effect size, right? So you could take this into account and choose a replication success metric that is a bit more suited for this type of project. And it simply helps us contextualize the reproducibility rates that we find. And one could also think about doing like sub-analyses of different types of study pairs, and then, compute the reproducibility rate on subgroups. The main limitation is kind of the current availability of the data. So all of these reproducibility project or replication projects, they usually publish their data, but the data that they publish is quite limited. So it's usually kind of the outputs of their replication efforts versus the original ones, but less so these type of covariates that we would like to see. So would be very interesting. For example, also one of our reviewers pointed out that it would be interesting to see a covariate that is directly linked to questionable research practices, but this we currently don't have. So the data that we used is was kind of collected for its simplicity and less for its actual interpretability. So if anybody of you knows of data that is already around, would be very interested in that. And so this is also kind of to be understood as a call for future replication efforts to routinely collect such information that could explain shrinkage and heterogeneity, and also maybe do such a kind of, maybe even as a sensitivity analysis, also look at these type of location scale meta-regressions on top of what they already do. So I just have my references here, and that's all I wanted to tell you today. So I'm happy to receive questions.